Hello, thank you for having me today. Um, so, uh, who am I? I'm Mathias, I'm the CEO of Ubique, and Ubique is a company that is specialized in consumer software, mostly mobile apps. You may know some of them. Also, today's topic, weather, MeteoSwiss app, which is not the topic of today, but which is one of our first and also biggest steps in the weather space. I was asked before, where does my enthusiasm about meteorology or weather comes from, and so I take this question and share it with all of you. So actually I grew up in the mountains, and I was a heavy snowboarder, and I always needed to know when are the conditions right, where is new snow. So that's why my passion for the topic started. And today I want to talk about Fluid Meteo. Fluid Meteo is our app, our global weather app, and I want to give you some insights, thoughts, challenges that we came up with or that we solved, and maybe also some that we did not solve yet through this. And I want to take you on this journey. So the question is, so how do you build actually a global weather app? How do you do that? And as always, you start with a empty screen. And so weather is something that is geographic. So it's inherently a geographic thing. So, okay, you put it, probably you need some sort of a map. So for illustrative purposes, I choose Switzerland here, but you could take any geographic extent. And so what do? You have this map and you put it on your phone, and then this is what happens. So the aspect ratio probably isn't that ideal. If you have this let's say more horizontal than a vertical geographical viewport. So the solution is then quite obvious, I guess. It's putting it landscape. Probably not. So we have 2024. Nobody uses their phones in landscape mode, except maybe for video, long video sessions. But even then, people use it portrait. So we need to find a solution in which this stuff works in a portrait mode. But then we have a problem. I mean, you see, this Switzerland gets a bit small, and then we have a lot of additional empty space. So this is when we decided, okay, how do we put this geographical output, this geographical content on our app? We will always have a lot of space for doing something else. And this is where we come up with our core concept. And here you also see the first visual or actual visual design from our app. So what we basically have is this concept, and we really thought this through the whole app. So you basically, every screen in the app is just this composition in which you have the map viewport, and then you have this meteogram. And we thought it is quite cool if you really combine these two concepts together. So you may say, okay, Switzerland, I said it's a global app. And why? I mean, there are other countries that are not of this shape, of this landscape shape, for example, Germany. But then you may, if you know that, maybe you know that weather is, at least in our latitudes, is inherently horizontal because of this west component that you have in the weather. We will later on see some weather scenarios in which I can make it more tangible. But this is a discovery that we have. So weather is inherently west-driven, means horizontal, and then we have this unfortunate constraint that the weather comes from here, but we have to. So this basically what holds for Switzerland as an illustrative example also holds for more or less all the latitudes in which weather happens. So I'm not speaking for the equator because this is a bit different anyway, but in the most of the So that's why we choose this approach. We said, okay, we do not need a full screen map because we almost always have this kind of this kind of property of this geographic screen. Okay, then I want to dive into this meteogram. What did we thought of here? We wanted to do this a bit different than we used to do, or that also other weather visualizations do. And I start first. You may notice the temperature profile. So I choose Boston right now as an interesting weather. So right now at Monday. So this is actually this week's weather in Boston. And I mean, you had at a glance, especially if you're used to the app, then you're also used to the color schemes, and then you have at a glance, I mean, you need less than a second to really parse that. Okay, right now it is somewhere greenish, then in 2 days it will be hotter, and then it will be back cold again, back to this. So, and this is something that if you use the app for a while, then you have like literally less than a second, and you see the week's weather, or whether there is a drop in temperature or a rise or something else. And the same holds for the precipitation. In this example, not really exciting. I mean, this is just a small amount of precipitation, but if you would have here a big precipitation event, you would see this also immediately. So this is what we thought. So you had at a glance, you see the week's weather. This is for the temperature, and also in terms of the weather icon. This is something that you're all familiar with, I guess, the sun and the clouds. But these are always abstract icons. So you have a sun, you have a small cloud, and you have a bit more the clouds, then you have grayish clouds and dark gray clouds. But this is always somehow schematic. It's an abstraction from what actually happens. And here we went one step back and looked at the raw data. And what the raw data that we have from the weather model, so the output from the weather model basically knows 3 layers. I mean, actually it knows a bit more, but there is like this well-known concept of these 3 layers, which is basically low, medium, high. And we do not just build a function that interprets this and then puts out an icon, but we directly visualize this. So what you see here is, okay, we have here, let's say on all levels, some clouds, which also means we have the precipitation here down there. And here we only have some slight high clouds, and here the sun shines through. So what we basically did is we used the same logic as you would do for a normal weather icon to determine whether there is a sun on it. And if this logic returns true, then we just show the sun, but the clouds are actually the raw data that we have. So you see here, I'll give you this better example, the one that you know. So this is so you can also make sure whether the prediction was right. This was made on Monday evening, as you see. So yesterday, if you remember, you had this window of non-fog time, and you see directly this is only low, so that means it's fog. So and then you see you have this slight window, this small window of sun. Today it was like somewhat. I mean, the sun really shine through, but I mean, the model predicted it somewhat correctly. So it was like still some clouds there, and then tomorrow probably not. And we hope then that the model has arrived for Friday, so that we have at least some sun. That's for the meteogram. Maybe one last thing about the meteogram part. You also probably you didn't notice, but when I say to you, you will notice. And there is no legend, so we do not have. I mean, for a normal, say, scientific graph, you would have a legend. So that you said, yeah, okay, here is 5, 10, 20 degrees, and then on the other side you would have a legend for the precipitation. And what we also thought is if it should be as self-explanatory as possible. So what we have is the temperature. First, we have the color scheme. Yes, you have to learn it, otherwise you don't know it. And the same basically for the precipitation. but what we do then is we do find locally the maximas and minimas of this. So this is not like the day max and the day min. It's really interpreting this somehow sinusoidal curves and finding the maximas and minimas, and then writing only these. Sure whether there is an example. Yeah, maybe here. So this is maybe a short artifact because there is slight hill here that you can see. But actually, the good thing is if you do not have this typical sinusoidal waveform of the temperature. For example, if you have a rainy day and then you have a cold front or something, then it may just drop and you do not have a day pattern. And then these min max temperatures are not really well suited. So the classical min max temperatures are not really well suited to give you the actual impression of the weather. And here you see basically the maximum temperature of this phase or this peak and of this valley then. And the same we did with the precipitation. We also do not have a legend here on this view, but what we do is for the persons that can interpret this, we have the daily sum. So you actually do not know what green means just by looking at this, but you see, okay, it's 4 millimeters. And if you are the kind of person that knows what the 4 millimeters of precipitation means, then you also can sort of infer what will be the intensity here. And so we could get rid of this and that had get a really clean visualization then. Okay. About the interaction, I will talk later on. So this white thingy there. So now we have a meteogram part. Then we still need the map. And this is actually really like this one. Beautiful map. It's from NASA. Really a lot of post-processing in it that you get this beautiful map. But this map, I mean, this is okay for this screen, but it has maybe some problems. So as you all may know, Antarctica is the biggest continent on Earth. It uses the most pixels, and you also know that Greenland is almost as big as the Sahara, right? Or maybe not. So there are better visualizations for the Earth, especially if you want to go and say, okay, we want to put the global weather systems. We want to see and interact with the global weather system. We also want it to be displayed as it actually is, and that's why this kind of visualization is way better suited. And then you also see when you go further, and then you start to interact with it. So you see then the first hypothesis of before, let's say, Greenland is as big as the Sahara, probably not, way smaller. And if you look at Antarctica, it's still a big continent that nobody actually, so that you do not really know a lot about it, but it is not as bigger than the others. So you really get a way better feeling when you go with a projection like this than if you would go with a squared one. So I just go back just to give you the impression. If you imagine putting here the weather system, and then you say some rain or clouds going from here to here, or precipitation from here to here, then you had the impression that the distance from here to here is the same as from here to here, which is obviously not. And I do not have an animation on this, but this always had this somehow, so this bad patterns on top and bottom where everything moves extremely fast, and then you do not really get how the weather system actually works. So this is a really beautiful map. I told you I really like it. It actually, you can have it from NASA for each month, just as a side note. So this is, I guess it's somewhere Octoberish, where there is less snow here, but you have also when it's with more snow powered use. Okay, so if you're interested in this kind of this, they are free available. But these maps are not really suited for putting weather data on it. I mean, if you have a lot of color already here, so distinguishing then the weather, I mean, maybe clouds would work, but everything else which you go into a color scheme probably don't. So we need another map style for that than just the satellite images. So then we come to hill shading, and hill shading is the term of how you do hills, basically how you draw hills in a mapping context. And I have you here the example of Google Maps. It's not the normal Google Maps, but if you find a setting, you can switch to this elevation mode or something. And here you have a more relief style hill shading. And this is what most of the maps do if they are going to visualize hill shading. And I'm not talking about the POEs, you just have to filter it mentally out. I couldn't do that in Google Maps. But if you just look at the background map, what you see is you have a lot of detail in it. And you see every small valley and also here like little high frequencies in it, which may be okay if you wanna go really deep into it and maybe you go for hiking or whatever. But if you are looking in a weather context and the weather data that we are going to visualize, the ones with the best resolutions are those from the radar, from precipitation radar, and they are like 1 by 1 kilometer. So it's like a pixel like that. So if you have this resolution and you have then a way higher resolution, so it really takes off so you have then a lot of noise in the whole thing. And also in terms of the style, this is probably made by, you just have, you model you have your elevation model. So for each pixel you have, like say, the height, and then you have the model, you put in a light source somewhere, and then you calculate how much light this reflect, and then you get something like this. Then you color it, then you have. This gives some kind of a metallic look, and also you have a lot of high frequencies in it. One way to get rid of the high frequencies is if you just get less a lot lower resolution. But the problem with lower resolution is I lose the resolution. I also lose the precision of it. But what I actually want is I want the precision, so that I really want to know that this hill here is there, because when I lose the precision, then I also lose the precision of my actual data visualization. But I want it to be way more clean. And there is a way to do this. It's actually more or less unofficially called the Swiss style. And for those of you that are into cartography may know this, or those of you that went into primary school in Switzerland, this is from the school book. So this is the way that also Swiss Topo does this hill shading. And you may, if you compare this, you see it's, I mean, the ridges of the hills, they're exact on the exact position, but you lose, or you want to lose, that's all these high frequencies. You have a way cleaner setup so that you can really directly see where are the valleys, where are these, so you can really the point that are relevant for the weather. It's not relevant whether it's here in this small thingy there, but it's relevant that you know, oh, okay, it's here in the Thunersee in this ridge here. So this is actually where we want to go. But now we have a bit of a problem, and this is Swiss Topo, and this Swiss means it's actually Swiss. So this is not a global topo, so we do not have this kind of map for a global thing. So we went on to find a way how we could do this, and it's actually not that easy because these are hand painted. So this is actually are the cartographers that, and it's not, you can just take a function and put in all the height data and then get as output this one, because there you have a lot of the expertise of the cartographer, and this is really an art, drawing this kind of maps. And there is, like, of course, they have styles and guidelines if you're a cartographer at Swiss Topo doing this. And so how do we do? I mean, we tried some approximations, but it was not that really, we were not so really happy with it. And we found then that some researchers from Australia thought the same and also wanted that that we like this Swiss style hill shading. And what they did, they had quite a cool idea. And they took, so we have 2024, they did it a few years ago, but so how did they solve it? They used machine learning for it. So what they actually did is they took a lot or maybe all of these hand-painted versions from Switzerland that they could find. I mean, they did it together with Swiss Topo, and used this as an input in a machine learning model together with the real height data. So they could train based on these hand-painted Swiss hill shadings. They could train a machine learning model that takes an arbitrary height map that you can input, and then as an output you get this Swiss hill shading thingy for whatever. I mean, for the moon if you want. So for any height map that you have. And that's what we did. They have a software. You can actually download it in the App Store, also in the Mac App Store. This exists. And it's called Edward, and named after Edward Imhoff, who is one of these fathers of this kind of hill shading. And this is then the result we get. So you can do a lot of parameterization, but for those, this is the valleys. These are the mountains that I had to snowboard. And so this is like the raw output you get from this. This is a part of Switzerland. Here also another part, Genoa. Here Genoa and Italy, the Alps, and then here the Po plain. And you see it. You have really a lot of these beautiful elements. So you have in the plains. You get rid of all the high frequencies. I mean, of course, the height model is not just flat here, but it really detects these small high frequencies that you do not want and flattens this out. But you get the beautiful valleys and hills. So yes, this is then what we have here. Then the next thing is we have now a cool background relief hill shading. What do we need next? We need some other layers. What we then did is we pre-processed. We took from OpenStreetMap and pre-processed different other layers, like as the borders and lakes, rivers, roads if you zoom in, and also the let's say the cities and places. And then as a next step, obviously we need to push then the data, and this is what it looks like in the end. When we have now a visualization that works for all over the world. So now it's time to put this stuff together, and this is then how it looks like, this combination of the meteogram we saw before and the map. Which is which uses then this upper part. And what we have now is we can really combine this. So that's the cool thing about it. So you have really, you look at this place, so you see Madrid, and then you see on the bottom part you see this week's weather for Madrid. You see that in Tuesday it does rain. And then you see also in the column there, you see that you had this part that we looked before. And the cool thing is then I show you afterwards the interaction model. But if you are interested, Saturday, cool, good weather, how will it be? Then you can just click on this, and then you see the map part counterpart. So you have really these connections with the projection on top that gives you the geographical 2 dimensions, and the projection in the bottom, which gives you the fixes the geographical dimensions, but lets you interact with the time dimension. And this is then how it looks like. So we visualize this then and do it really. So we really wanted to go push the limits here, so that we do not only have this as a still image, but also do like very heavy interpolation between the images. So it's not only on a geographical level that we interpolate. So you see here that we do not have any pixels or stuff here. So it's really the model output, the model grids are interpolated in the two dimensions of the two geographical dimensions, but also in the temporal dimension. And this gives them these fluid animations. Yes, so you see here the system that you see here. It's unfortunately not that a fortune, but you see here this low pressure system over Spain, which you when you start in the local thing, you see, okay, that's my local weather. But when you zoom out, you start to realize that this is a part of the bigger system. And actually, maybe you heard it in the news, were some floods due to this low pressure system. And so you get really this connection through from this local to this global view. So then next, I think I'm going to show you. I will show you some of the things then in the app, how it then turned out. So this Madrid example we saw before. So what we can do is obviously the interaction on this model. So we can really go from the local to this total global mode, and then we can have a look at the weather system on a global scale. Maybe I show you this temperature layer. Here you can really see the global weather system. If you have a look at it. So if you go, for example, here, you can see this, so you see this west component, by the way. So you can really see on this, so how this weather system behaves. So, and the cool thing is that you can really have a tangible way in navigating through this system. So, and you can also have, let's say, projections that you did not really, I mean, nobody looks at the North Pole, so it's really a projection you also have to get used to. And then you see here really how this weather system turns around in this west to east manner. And then you see these outbursts from the jet stream. And so you get to really get to feel the global weather system. And the cool thing is also what we try to do with the app is somehow educate people a bit more. I mean, this is, of course, a lot. It's really technical in some sense. If you look at the temperature layer, this is not ground temperature. This would look different. This is the temperature at 850 hectopascal. So this is somewhere at around 2,500 meters. Why do I show you this layer? This layer is at an altitude in which the atmosphere is not really dependent on the time of day, because the sun let's say the sun that heats up the ground, this is enough. So this is enough high that it doesn't have that impact. So you can really see the energy in the atmosphere directly and not being influenced by this daily thing. So you can see, for example, if we go here to Sofia, you will see here, okay, it's going to get cold, so you have frost in the end of the week. And then if you compare them here on top, and you go, then you will see, okay, you see really this cold air coming down there. If you would have a look at the ground temperature, you would just have this one. And this is, let's say, some disco thingy, because you have the day. I mean, it's also nice to look at, but you really don't get this weather system feeling. So this is then also the control that we have. Here you can choose the different layers, for example, temperature layer, or also precipitation, or if you want to go clouds. You can see the clouds here. Maybe we want to go to Taipei. It's an interesting weather situation there currently as well. Oh, I lost it. Or you lost it. Oh, I lost the internet connection. That's the problem. No, I'm on the mobile. That's probably why. So I'm back, but I need to share again. Yeah, so I'm back. Yeah, you see here in Taipei, yeah, this gets a bit compressed away. So, but you would see here the eye of a typhoon. Maybe I just switch directly the adds the precipitation, so you see it better. And so you can also see here really how the visualization is beautiful for this kind of weather system. So we can go here and then see here this the mountain ridge that blocks the typhoon when it has the landfall in Taiwan, and you get also feeling of of this interesting path. So you see here, okay, this is typhoon. When you're interested, what happens actually to such a typhoon afterwards? I just scroll a bit into the future. So when you're in Tokyo later this week, the rain that you will have will basically the basically the ancestors from, or the descendants of this typhoon. And then if you go a few days further and go east and east, then you will see it hits them at some point, Alaska. So I think this is something that's really beautiful in this visualization. So you really see that weather is a global system. It's not just something that happens just here. So you really get this connection, so that this, I mean, we had also the same for these hurricanes that hit this year in the US. And then you could follow them and see, okay, this weather change that will happen in the end of the week was basically the hurricane XY that was that you heard in the news the week before. So I'm switching back to the presentation. What we need also in order that we in order to build this app is of course the data. And where do we have this data? We had some luck because not only we, because the European Union had made this cool directive which is called high value data set. Maybe of interest of you anyway, because it's as you can see, there are a lot of different sectors that are covered by this high value data set directive. And you see here also the important one for me obviously is the meteorological. But what this directive actually says is that by this summer, so 4 or 5 months ago, each member state is obliged to do deliver this kind of data as open data. So what we actually have, we have a situation that we in Europe have more or less from all the data that are gathered by the weather services, and these are mainly radar data, or also the weather models the output of the weather models that they produced have to be accessible to a form of open data. Switzerland, as it is not in the EU and is always a bit late, will be ready at April 1st, 2025, but they will have the same data open as well, but it still will be in April 21st, April 1st next year. But this is the theoretical part, but the reality is a bit different because yeah, you have a lot of member states. Not each of the states is as fast as, let's say, Germany, which were actually the first and had a really good portal to get this data, which, by the way, also delivered the data for the global model. And so was quite a lot of work to gather all this data from these different sources, and also is still quite a lot of work because we have to monitor this thing when they change something. We have to look at the communication that we have some channel that we know if something changes. We have not right now. We have the problem that Italy has no data because of a flood. They had a quite similar weather situation as Spain right now, and they actually had a flood on their supercomputing center. So this will their model does not run right now they said during the next week or so it will be up. And so you see we have, let's say, if you have like these really different kind of data streams, you have to hassle with this kind of problems. Maybe this will be resolved in the future. There are initiatives of a European Union-wide platform that does this job of gathering this data. But right now we are in this heterogeneous world, and this is why a lot of work of ours goes into gathering this data and then showing it. And this is, by the way, also the strategy that we follow for the application as well. So we have this global model from Germany, and then we go each country or region by region in which we enrich the application. So by adding more and more countries. Yeah, this is what I just said. So we have, let's say, two different sources of data, or two different places where we visualize data. One is the map, and the map has total different properties of the data processing, because the map, we deliver a lot of data because you basically have the whole planet. But what we still want is having a resolution, the best possible resolution for each of these, for each point of view. And what we have here is a system. Crash. Have a system in which you always have the best quality at the focus point that you have. So what we basically did, maybe you notice it if you're into this stuff, you saw we do not have a tiling. So it's not as you have from, I mean, we have it for the background maps. When you go, then you see these tiles that are getting loaded and one after the other. But for the weather layers, we do not have a tiling. What we have is a custom projection that makes sure that the point that you look at always gets the best data. And then as more as you go to the peripheral places, you get less. So maybe if you look here on top, yeah, you cannot really see it because of the compression by zoom. But when you look at the app, then you will notice that here at these peripheral elements, you still see the weather systems that are flowing, but they have a lot less resolution in this view, because I do not need a lot of resolution for just having these few pixels that I draw. So that's basically how we did, how we solved the whole data problem of the globe. So this was also quite a challenge that we solved. And the cool thing about not having a tiled visualization is that you do not, I mean, you can have an animation like this. If you have a tiled architecture, then you would always need to make sure that you have all the tiles when you go one step. I mean, one is being only manipulating the geographical dimensions. Then you just reload just load all these tiles. But when you start switching the temporal dimension as well, then you have really a lot of complexities to solve. And then it really goes out. I mean, we first had this architecture and it just did not work out well. So you could not really have this. So either you waited until everything is loaded, but then you have a really latency problem, or you just start, but then how do you interpolate between steps when you do not have a tile loaded? I mean, interpolation in the time-wise, but also geographical. So that's why we did this for this architecture. And here the pipeline is a lot about having an architecture that really reduces data, because we need to ship a lot of data, really have a lot of compression, but without losing any significant visual complexity in the data. So this is how about the problem of the map, whereas the problem of the meteogram is then totally different. And I show you, I'll come back to this later. The problem of the meteogram here is totally different, because data amounts are not a problem anymore, because I fixed the geographical location, and then I only have a time series. And compared to this whole video imaging stuff, this is always negligible, the amount of data. But what we solve here is that we want to have a accurate as possible prediction. If we just would look at the global model as we have here, and then just say, okay, I take this point and plot this, then I would not have, let's say, really a good prediction. So this is why we have our fluid weather prediction engine, and we solve this architecturally, that this is, we have an architecture that this is all evaluated on the device itself. So what we basically do is, when I start the app here in Zurich, then I have, this was what we have here, then I have this location, and then I'm really here at 420 meters above sea level, and I'm really at this very point where I am right now. And what we need, so you see our office is 10 meters lower, obviously, than the others. So what we then use is this information of the height, because, you know, if you are going higher, then it's getting colder. And we have, let's say, really a prediction for each 90 by 90 meter patch for the whole world. And then what we do is we take the best weather data that we have for this very point. So in this example of Zurich, you cannot read this probably, but I can read it to you. I mean, this is just a debug view, so I can show you as a user, you don't see that. So what you see here is that's past. The greenish thingy here is radar data, because this is obviously the best data for precipitation. For this visualization of the clouds, we use the model data, because we have the different height layers. On the map, we use satellite images, because we only have one height layer. Then when we go to this step, we see we have ICON D2, which is a German high resolution model. And this D2 stands for, also 2 stands for 2 kilometers, which is quite a good weather model. And that also gets more local, a better local feeling. And then we have the ICON Global, which is a global model. But here, this is a higher resolution one. Then going to the next, which is a lower resolution one, which you see here is, if you look, then you see here only these 3 hour or 6 hour, 3 hour thing. So it's a bit edgier than here, because this model is so you see the data gets less and less accurate, obviously, because the weather models are tuned like this, so that you get a higher resolution in the beginning. And what we do is basically feeding all the best weather models for this very point. Then what we do is calculating a prediction that basically takes the data of all these models, and then adding additional information as the height information, and then correcting it for that as well. And so we get a prediction for this point. And the cool thing about that is that we do everything from that on the device. And that's cool for 2 reasons. First is privacy. So we do not share the location with the server. We do the only thing that we actually know is that you had selected a point. For example, when I push London, you don't see the screen anymore. When I hit London here, then I get the best predictions. And so I get the points, the model output that are in the vicinity of London. So we may infer that you're somewhere in the model scale region of London, but I do not get a position. I also do not know whether it was this data gathering was because I clicked on London, or whether it was in my position. So that's the first thing, that I can really get a totally accurate prediction based on your location without revealing my location to our servers. And the second one, that it is super scalable. So all these calculations that you have to make. I mean, if you have 1 million clients, the only thing that we need to make sure is that we can get this data somehow out. But that is actually a solved problem. Providing static data is not hard, but calculating and have a lot of servers, that would be hard. And then we just offload this to the client. So here I have a different one. Forte, I don't know how to pronounce this, somewhere in Norway, but I wanted to have this for you as illustrative purposes. You see here you have different models then for the Nordic regions, which then lead to other things that you can also see here. These other patterns, more precipitation, just to have another thing as well. So that's about it. And I think it's time then to have this beautiful video. And if you have any questions, then I would go to the question and answer